Alright, this video lesson is going to focus on covalent bonding and the molecular compounds that contain covalent bonding. Covalent bonding is going to occur when two or more non-metal atoms are going to share electrons. These bonded atoms actually become a part of each other chemically, so this makes for a much stronger bond than our ionic compounds that we learned about in the previous unit. So you can see here as individual atoms, they're then going to go ahead and each share an electron with the other atom in order to complete their octets and become more stable. Depending on the number of electrons shared between two atoms, we can consider a single, double, or triple covalent bond. Single covalent bonds involve exactly two electrons or one pair of electrons, so we represent it by a single line. So with H2, they share two electrons, so we represent that with a single line or single bond. Double covalent bond is going to involve four electrons being shared between two atoms, so two pairs of electrons, and we represent that by two lines. So here with O2, which is a common double bonded molecule, we have four electrons, so we're going to represent that with two lines to represent our double bond. And then finally, N2 is a very common example of a triple bond, which involves six electrons shared between the two nitrogens in this case, which is three pairs of electrons. So here we have a total of six electrons being shared between each nitrogen, so we need three lines, each representing two. In general, triple bonds are incredibly much shorter and then because of that much stronger than a double bond, so it means it takes a lot more energy to break them in general. And much more stable when they form. A double bond is much shorter and stronger than a single bond. Alright, so we're going to go ahead and work on drawing Lewis dot structures for molecular compounds which contain these covalent bonds. With molecular compounds, they're going to look very different than ionic compounds. There's no charges. We're going to be using lines to represent sharing. So you really want to work on the differences between ionic compounds versus these molecular compounds. Now you will hear me say two different terms. One is going to be, when I say lone pair, you have to know that represents an electron pair that is not involved in bonding, so a lone pair only show up on certain atoms. And then bonding pairs are electrons pairs shared directly between two atoms, which you'll see represented with lines. Now, I'm not going to go through these slides because you're going to hear me go over them as I do the examples, but you do need to fill in the blanks here, such as counting the total number of valence electrons, picking out my central versus terminal atoms, using lines initially between the central and terminal atoms, distributing electrons on the outermost atoms first, then depending from that point on, if I have extra electrons or if I've run out of electrons, going ahead with those steps. So with our first example, which is the most straightforward one out of the three, we have CCl4. So I'm going to add up my valence electrons. Each chlorine has 7 valence electrons, so I have 28 there. And then carbon contributes 4, so I have 32. So I have 32 electrons to work with. I'm going to decide where they go. So I'm always going to start with putting, in this case, carbon in the center with the 4 chlorines around it. Start with a single bond between the center atom to the terminal ones. And you can see I never connect the terminal ones in any of the examples we're going to do in this unit. So I'm going to subtract out then 2, 4, 6, 8 electrons, so I have 24. You always start on the outer electrons first until we run out of those 24 electrons. So I already have on this chlorine 2 electrons in the bond, so I need 6 more. And I can see that my other 3 chlorines also need 6 more. So since I have enough, I'm going to place 6 electrons on each chlorine in order to complete their octets. So I place 6, 12, 18, 24, so I have no more electrons, which is a great thing for this particular example because that means I'm all set because I still have 32 electrons on my structure. Carbon has 2, 4, 6, 8 around it in the bonds, and each chlorine has 2, 4, 6, 8 around the bonding pairs and the lone pairs. So this is a complete structure for CCl4. All right, now we're going to look at NH3. So I'm going to add up my electrons, in this case with the nitrogen and 3 hydrogens, each contributing 1. I have 8 valence electrons. Nitrogen is going to go in the center. Hydrogens should always be on the outer part of our compound. Just like before, I'm going to start with just a single bond between the center and outer atoms. So that contributes 2, 4, 6 electrons, so I only have 2 left. Now, hydrogens are complete with the single bond. Hydrogens only need 2 electrons to be full. You should never ever put lone pairs on these outermost hydrogens. You leave them alone. That means then I have extra electrons. Those extra electrons we're always going to place in the center on, in this case, nitrogen. So now I've used up my last 2 electrons. I have 0 left. Each of my hydrogens are full with the 2 in the bond, and then I have 2, 4, 6, 8 electrons around nitrogen. So that is a complete structure for NH3. This last one is probably the most complicated for students out of this 3. I have CO2, carbon being in the center, so we can make it symmetrical. We're going to add these up so I get 16 electrons. So I'm going to start first by placing single bonds between the carbons and oxygens. That's my first 4 electrons, so I have 12 left. I need at least 6 on each oxygen, so that makes sense. I have 12 left, so I'm going to place 6 and 6. Now I'm out of electrons at 0. So if you check the structure, while I still have a total of 16 electrons, carbon only has 4 around it. So I'm going to take off pairs of electrons on the outer atoms and move them to create a double or a triple bond. So I'm going to first remove these 2 electrons as a pair, and I'm going to make them and move them to be a line between the carbon and oxygen. Now this is great for this oxygen. It still has 8. And while I've moved carbon closer to 8, I'm still only at 2, 4, 6. So now I'm going to do the same thing with these 2 electrons on my left oxygen. So I'm going to erase those and place them together as a line between that oxygen and the carbon. So when I check, I have 2, 4, 6, 8 around each oxygen. So those have a complete octet still. And now finally carbon is complete with its 2, 4, 6, 8. So I still have my 16 original electrons, and then everything has a complete octet. All right, a couple things you might want to keep in mind is some of our very common atoms that we use is just knowing how many bonds they can form. It kind of helps you create the structures a little bit quicker. If you look at a hydrogen's dot diagram, it has 1 unpaired electron. So we only actually need then to make 1 bond to hydrogen, which we saw in NH3. If we look at fluorine's dot diagram, same thing, I have just this 1 unpaired electron. So we're going to find that fluorine and our other halogens tend to only create 1 bond in structures. Oxygen has 2 unpaired electrons, so you're going to find that oxygen, in all the examples we're going to do, is always going to make 2 bonds. Same thing with sulfur in the same group as oxygen. Nitrogen, which will have 3 unpaired electrons, actually then is going to most commonly make 3 covalent bonds. And finally, carbon, if we what we call hybridize these 4 electrons around evenly, we see that we have 4 unpaired electrons. So we're going to find that carbon is always going to make 4 covalent bonds. So you might want to jot those elements down for yourself just because it makes it a little bit quicker and easier, and also a way to check that your structures are correct.